Okay, so now it's 11:15. Now I got the time right. So Pedro is just started a postdoc at USP, so you will see a lot of it, a lot of things the next 2 or 3 years. 2 years. Okay. Yeah. So this is a good time to let us know about your research and maybe to start interesting physics discussion. So we in the afternoon we'll get talked by another new postdoc, same apply there. So please take the group. Thank you.
Hello everyone. So like Turani said, my name is Pedro Rossetto, and I'm going to talk about continuous gravitational waves from neutron star and map. So a quick outline of the talk. I will give some background and motivation about the problem. Then I will talk about magnetically confined mountains on neutron stars, and then the continuous gravitational phase. I just wanted to do a little bio about me. Sorry, I won't spend long on this, but I'm from Brasilia, the best city in Brazil. The airplane city. This is the same place 6 months apart in our 2 seasons, dry and wet. So I was born and raised in Brasilia. In 2013, I started my bachelor's and teaching degree there. I had a small time in Canada, Queen's University, and I studied with Dr. Martin Duncan in planet formation. Then I went back to Brasilia. I did my master's degree there with Professor Ulloa on PPA spacetimes. Then I went to New Zealand. I hope you guys recognize this. And I did my PhD there in 2020 when the pandemic started. And I was working with Professor Jörg Fraundiner and co-supervisor, sadly remotely by Andrew Melatos because of the pandemic. And we were working on magnetic confinement on the neutron stars. That's what I'm talking about today. Then I went to Australia and I was working with Andrew in person this time and at the University of Melbourne, just doing some stuff, keep going with some stuff in my PhD. All right. And now I'm here in São Paulo, and I work with Diego and with the group of PhD, the high energy astrophysics. All right. Enough about that. So some background and motivation on the problem. Neutron stars are sometimes found in the systems called low mass X-ray binaries, which is a binary system where you have a low mass companion to the neutron star, and because they are a bit too close, the companion star loses mass to the neutron star via Broglie overflow. Then you form this. How do I do it? Yeah, you form this accretion disk around the neutron star. And the systems are interesting, and they give you 2 kind of problems. First one is, why do the neutron stars here in the system do not spin faster than we observe them spinning? And because a simple calculation that you do of how much angular momentum is being transferred should give you the neutron star spinning faster than we observe. And the second thing is that if you somehow measure the magnetic field here, you see that it's much lower than the isolated neutron stars. So why is this magnetic field lower? Here's some observational data. Not that I do much of that, but I just wanted to show. So some sources, the value of the magnetic field, the period, and the created mass. The period here, I say, why do they not spin faster? But they spin very fast. They're called milliseconds.
Sorry, I don't understand the tension between expectation and observation. Why the expectation should be equal to observation?
If you do some like basic calculation, or because the observers can calculate the accreted rate, the accretion rate, and then luminosity, and then you get that and you transform into angular momentum and how much angular momentum is being transferred to the star, and the star is, I don't know, like 10 radii, 10 kilometers of radii, you should have some very fast spin, and actually it should be breaking apart the star over 100,000 hertz.
Yeah, but then that requires the knowledge of the inertial moment, no?
Yes.
That depends on the structure.
Yes, there is many details that it's just a simple calculation would suggest otherwise, but of course, if you do some more detailed modeling, you see that that's not the case. The answer is pretty much you have the jet, and the jet is taking away angular momentum. But yeah, so about this, we need a mechanism to make the star lose angular momentum. And as I said, there is this electromagnetic jet that carries away angular momentum, but you could have one of the more exciting possibilities is gravitational wave emission and losing angular momentum to gravitational wave emission. And for a rotating star and for gravitational waves, you need a time-varying quadrupole. And for a rotating star, you need a non-axisymmetric deformation. If it's completely axisymmetric, it doesn't emit gravitational waves, right? And this deformation is what they call in the literature mountains. You see the size of the mountain. All right, and how do we form this mountain? So there are two types of mountains that I classify. There are the elastic mountains and the magnetic mountains. The elastic mountains, they are deformations of the crust. So the star is spinning, there's some deformation, and the crust holds this deformation in place. And there are the magnetic mountains, which I'm more interested in. And these magnetic mountains, yeah, okay. These magnetic mountains, they are present in both. They're present both in isolated neutron stars and accreting neutron stars as the low mass X-ray binaries. And in isolated neutron stars, it's maybe more relevant for the case of magnetars, where you have a very strong magnetic field, and magnetic fields cannot be spherically symmetric, right? No monopole. So the star has some deformation. A fluid star would have a deformation. And this is a very favorite animation of mine that was made by the group in Australia that shows studying this now that the animation works. It didn't work at the conference. So it's showing a low mass X-ray binary, the companion star losing mass, forming the accretion disk, the neutron star rotating, and emitting these gravitational waves, which of course not to scale. Yeah, so that's what I'm going to talk about. The magnet. So you have the accretion disk and the neutron star in the middle, and like far away in the accretion disk, the matter is following gravity of the neutron star. But when you get closer to too close to the neutron star, the magnetic field starts to dominate the dynamics of the system. So the plasma of the accretion disk is going to start following the magnetic field lines. So at the moment of accretion, this matter is going to be coming from the magnetic poles. And then you start building up your mountain there on the magnetic pole. And because this is a plasma, it carries the magnetic field. And what happens? Well, gravity does the thing and tries to smooth out your star to be spherical again. But because the plasma is carrying the magnetic field, there's some magnetic reaction, magnetic force. This is just a very qualitative picture that will go into the math soon. And hopefully you should have this balance between the magnetic force and gravity, so you can hold the mountain in place. So this model has been studied in Newtonian mechanics for many years now. And now I will explain what they've done a little bit. And the basic thing is that you get equations of magnetohydrodynamics, which is the continuity of mass and the fluid equations, plus Maxwell's equations. You have Ohm's law, you have the Poisson equation for the gravitational field, and then you do some spherical calc, some approximation. Because the mass of the mountain is much smaller than the mass of the neutron star itself, in Newtonian you approximate the gravitational field by this thing here, and you consider the system to be axisymmetric with respect to the magnetic axis, not rotation axis. Again, if it was rotation axis, no gravitational waves. We consider a colloidal magnetic field. So when the magnetic field is colloidal, there's no toroidal component. You can generate the magnetic field by these two things. Phi here is the spherical coordinates, and psi is the scalar field that we are interested in.
And this is the first time I see the magnetic field parameterized in this way. Can you give some more detail why? What was the physical situation in the scribes? Why?
Yeah, can I write?
Sure. You can link us to my.
Yeah, that's right. So I think of these terms in a bit more generic things, but you can write the magnetic field as something like that, right, of the vector potential. If you and then there is this boloidal toroidal configurations, which is basically the boloidal are the classical dipoles that go in this direction.
So that would correspond to a magnetic dipole, the source of energy, like what?
Yeah,
The magnetic dipole oriented like the Earth. Yes.
But you could have also what they call toroidal components, right?
Now, the toroidal, I usually associate with the magnetic dipole like that, no?
No, the magnetic dipole creates the boloidal from pole to pole. The one in the
so if I have a J, say if I have a J, no, along the axis, that would generate the toroidal.
Yes.
And but then if
I'm talking about the dipole.
The magnet,
the current would be like that. Yeah. Yeah. So I'm for this model, I'm excluding toroidal components, and then you have a lot of symmetries. So if you have this vector as the axisymmetric killing vector, you have the Faraday tensor would be zero, the derivative of the Faraday tensor in the axisymmetric, and then this imposes lots of conditions here. And when you open it up, you get the most general magnetic field with no toroidal component being able to be written like that.
So psi is a scalar
field. It's a scalar field.
And phi is the coordinate.
And phi is the coordinate, yes.
And what the length of phi and one points in phi.
Yeah. So the
difference is orthogonal to phi.
Yeah. Yeah. So what is and this approximation is because normally we see these things as dipoles, but it's like it could be better. This is a first model. We also consider this system in the ideal MHD case. So we consider the fluid to be a perfect conductor. Conductivity goes to infinite. And we have involved the system in steps of magnetostatic equilibrium. So at every quote unquote time step, the mountain is in equilibrium, and then you tweak it and evolves a little bit. And this has also some motivation. The alpha band time scale is much smaller than the accretion time scale, but I don't want to go into those details here. Okay, and then when you take all those assumptions and put into the equations, run some math, you get this equation here, which is called the Gravitational equation. Is the equation of magneto-hydrodynamic equilibrium. This operator here, delta star, is this thing here. If you are very familiar, yes?
You mentioning the equation of state, so you need to have a model for the internal composition of different stars. That's relevant.
No, almost. Yes, I forgot to mention. For you to close the system, you need an equation of state. But I'm talking about the mountain itself. So it's the equation of state of the mountain, the matter that is falling to the neutral star. It's not equation of state of the neutron star itself.
You don't need to worry about that. This is inside the neutron star. All you care is
More or less,
its
yes.
gravitational field and the tiny bit of matter that comes on board.
Yeah. So for this model in particular, yes, we don't need to worry about the model of the neutron star inside. We are just assuming that the neutron star has a dipole magnetic field, and I didn't put here, but like boundary conditions, you impose that the magnetic field at the surface of the star is not changing. So it's anchored in this very like hard crust, but it's for the mass of the mountain, not the neutron star. Yeah, so this is a Gaussian operator. Feel free, anyone, to ask questions anytime, as we're doing. The Gaussian operator in spherical coordinates, it's written like that. If you really like Laplace equation, you might think that this is the Laplace operator, but it's not. The signs here are inversed in the Laplace operator. So you have your equation for psi. And because this is an equilibrium system, this psi here, which I showed you that it is the scalar field that generates the magnetic field, but it doesn't just define the magnetic field, it defines everything in the system. It defines the pressure, it defines the temperature if you want, or the density, because the system is in equilibrium. So in a way, you can think of it as like turning the equation thing and psi defines everything about the system, kind of similar. Psi defines everything about the system here. Okay, so what about the right-hand side? That's a source term that before people were just kind of guessing. It's like, oh, it's going to be something like that. But this model by Andrew, he was able to put this in a way that was a bit more consistent. So you're still going to have to define something, which is the mass to flux profile. So how you're distributing the mass into the flux tubes of your magnetic field. But after you do that, and this comes from the accretion dynamics, you can calculate this function f, which is the source term.
So is that a thing called a differential equation?
Not exactly. It is a nonlinear differential equation, elliptic. I will tell you why not an integral equation. Well, yes, because psi is here, so yes, yeah, it would be, yes. It's a very hard equation, as you can see. I don't have it here, but when I talk about the GR model, I will show how we actually solve this in detail. Okay.
Why is n a function of psi? Isn't n just the mass of the neutron star?
No, yeah, okay, I should find this thing a bit more here. So if you imagine the neutron star here and some of the flux lines. Very good questions. Thank you. So by the way that you calculate, this is the magnetic field lines, and they are, if you think about this carefully, they are surfaces of constant psi, right? So this is like psi1, psi2, psi3. So what you need to define when you put the mountain here, you said my accreted mass is like say 10⁻⁵ solar masses. And this thing here, m of psi, is how you are distributing this mass through the flux tubes. So you're putting more mass on the poles and less mass in the equator, exactly because the accretion disk is here, the mass is funneled to the magnetic poles of the sun.
You showed before the Newtonian potential appeared in the right-hand side, right?
Where?
Phi exponential less.
Yeah.
That's the Newton potential of the star.
Yeah.
So there's an M here which is not the same as this one.
Yes. There is the M of the neutron star, and this M here is another one, is the mass distribution.
So in this case, the mass is a function of psi, it's some prescription that you're providing, fixing it from outside some reasonable ansatz, or is it something that you're solving for also with?
Very good question. No, we are prescribing some M of psi, which is, let's see if I'm going to remember. Well, I'm not going to remember the formula itself. There are some exponentials and things, but it's basically something like that.
So mostly it would be accreted through the pole of the magnetic plane.
Yeah, you put most of the mass into the pole and less mass in a smooth way through the equation. This is also a drawback of the model. You can improve this. You can run some hyper simulations to see how the spins are accreted. But yeah, so as I said, this was the first model is isothermal, and it was done by Andrew and one of his students in 2004. And they got these two results, which I find very nice, which answers the kind of the two questions that I proposed. So one is the normalized magnetic dipole moment cumulative with radius, it decreases, and the mass ellipticity increases. So you see that just this modeling explains the two things, the decreased magnetic dipole and the increase of ellipticity, which would generate gravitational waves and break the system. This, by the way, is called magnetic burial. So you're burying the magnetic field into this mass. And then several improvements were made in the Newtonian model. I could spend another talk just talking about this, but I highlighted some here. There is the equation of state. This is the most important one, I would say. If you model this equation of state of this mountain a bit better, the ellipticity reduces quite a lot, 3 to 4 orders of magnitude. You look at mountain stability, this MHD stable configurations, you should always be a bit doubtful because MHD is very nonlinear and disrupts. Yeah.
Of course, on these dynamic questions are important, but you keep saying Newtonian, but why not solving the GR equation?
That's what I do. Right next. I'm just introducing the problem in Newtonian, and then I will talk about it. Yeah, so mountain stability, the mountains are stable, and you thought that it wouldn't be stable, but it actually is. And crystal sinking is something very interesting as well. These mountains then would start to sink into the neutron star, and then you would have to start thinking about how this matter interacts with the neutron star matter, and then you need the neutron star's original state, at least for the crust. Okay, and that decreases the ellipticity by some tens of percent.
The equation of state deep inside is very important constraint that in the past is it fairly well-known physics.
Maybe someone else can answer that, but I believe so. I think the big mystery is inside the neutron star, but in the crust we have some better ideas. That's what I know from the nuclear physics people. Okay, so what did I do and what was my PhD? So my PhD project was try to describe this whole system in GR, right? The neutron star is a compact object. The relativistic corrections should be important. And so that's why I was in New Zealand with the GR guy. He was very much into GR, knew nothing about neutron stars, and the other one knew a lot about neutron stars, not as much as about GR. So I was doing the bridge. There was the pandemic in between, but oh well, you do what you do. So in how does this problem start in GR? So you do the math breadth conservation, the conservation of energy momentum. So these are GR magnetohydrodynamics. You have Einstein's equations for the gravitational field, and you have Maxwell's equations. I like this formalism. But what are the relevant approximations that we can use to model the system in the same way that they use some approximations in Newton? So the first one is, again, consider that the mass of the mountain is much smaller than the mass of the neutron star. So you have the Schwarzschild spacetime generated by the star. And this is just to model the mountain. Have this in mind. And the phi here, m star, the fluid is a perfect conductor, so you don't have, in the reference frame of the fluid, you don't have any electric fields. The system evolves in quasi-static steps of equilibrium. So you have that the before velocity of the mass is just proportional to the time vector. The system is axis-symmetric, again, with respect to the magnetic field, not the rotation axis. And so the lead derivative of any quantity would be 0. Yeah.
So when you say that in equilibrium, geologic evolution, are you using, are you assuming that in addition to anti-symmetry, you have a stationarity? You evolve basically slice by slice.
You are not stationary per se. Yes, stationary per se.
Is T a time killing vector?
You evolve the system in a way that it's very slow. It's the adiabatic approximation. So you do, when I talk about the numerical, it's going to be a bit more obvious. So you're evolving this in steps of equilibrium.
So over a dynamical time scale, which is very short compared to.
Yeah, so the dynamical scale of the system will be the Alfvén time scale, the propagation time scale of the plasma waves. But the accretion time scale is much bigger than that. So that's why you have equilibrium. That's a good question.
Maybe
Yeah, yeah. The magnetic field is poloidal, so you can write it like this. Again, only psi matters. Things here, coordinates, and this a killing vector. Axis-symmetric killing vector. And then what do you get? You get the Gravitational equation again, but the GR version. And when you write this in Schwarzschild spacetime, you get this operator. And if you see, the only difference is this term in red, which is very important. This is going to still be an elliptic equation. This is not going to change characteristics because you never go inside the horizon. Yeah.
So we still keep learning with it. So in principle, this is a wave equation up there.
Here,
That's like a double in the variation.
it's not.
No.
This
The first term in your.
yeah. But this is the wave operator. Yeah.
It's wave variance.
Yeah.
So then you read, when you say that.
When you subtract these terms, you cube the time.
Yeah. Okay.
Yes,
you,
but this
you
is
don't
not
have
like
any
double, right?
wave-like behavior. That's why you end up with an elliptic equation.
Yeah, exactly.
Without having to assuming stationarity.
Yeah, without assuming back in. Yeah. If you write this thing in Newtonian, it's like kind of the same, but there you just have the three spatial components. You still have the covariant derivative. This is written in a completely covariant way, so you could throw any kind of metric there if you want. All right. And then you have the Gravitational equation at the right-hand side, which is the source term. So this is something that I did. So if you do these corrections and you calculate this by this function dm psi that I was talking about there, you get this. There are some corrections that come here from the sound speed. But in general, the form of the problem is very well maintained when you go from Newtonian to GR. There's the corrections, but the form of the problem is well maintained. And how do we solve these equations? These equations are, by the way, very hard. They are elliptic PDEs, but non-linear because of this term. This term is computed by this integral that has the variable here. So hard stuff. And the way that we do this is by this numerical scheme. So you solve the Gravitational equation by successive over-relaxation, which is a method that solves elliptical equations. But how do you know the right-hand side of the Gravitational equation? Well, you need to calculate first this thing and what you do for psi. So first thing you do is that you give the psi of a dipole, then you calculate the source term, then you have a Gravitational equation which you solve, and then you have a solution that you under-relax, and then you put it again in the mass flux constraint, and that gives you a new source. Then you put in the Gravitational equation, solve it again, new function, do that over and over, and the mountain evolves. This is what I was telling you about the quasi-static steps of equilibrium. So this is how the system evolves with time, not actually time, iterations, but this is how you get from an equilibrium to the next.
This procedure was just to, like a numerical scheme to stop the.
It is, but it has some.
It has some physics.
Yeah, if you go through the text, it is a proxy of the time evolution of this system, this numerical schemes. And we are starting from a dipole and ending up in some other kind of configuration.
There is not an equilibrate to sound.
It reaches a final equilibrium. Like that's the thing, the important thing.
Let's going to be at least conceptually what's going on here. So one of the assumptions is that this M of psi is something fixed, that you are not evolving in this iterative process. Something it's
What is
the mass that is being accreted through the flux lines. So that's not something that would be dynamic in the solving of the PDE. Then also, I guess that you need to put some initial conditions for the shape of the mountain.
Yeah, which is exactly this dm psi profile. And this is very important because this profile is physically motivated. The things that are in the pole and things, but this, because of the ideal MHD condition, this won't change because the plasma is carrying the magnetic field, and even though the magnetic field is being distorted, the amount of mass inside each flux tube would be the same.
So that would set the initial conditions for the mount, for the mountain that you're having there. Won't change when you iterate that scheme, but the shape of the mountain itself will.
Yes, exactly.
And the other assumption is that the magnetic field lines are always fixed and set it because of the structure of the neutron star, and they are not affected by
no. They are fixed at the surface, but throughout the evolution, it does deform.
Okay.
I will show the form of it. I might go a bit over on time because of the question.
No, that's part of it.
Yeah, it's fun. It's fun. I like being discussing here. So this is just showing you that the system does evolve to some kind of final state. This to run, well, to run this for long, it does stabilize. But here you see that already went. This is the change of psi per iteration. And it already goes to a very small number. And this is a fun thing that you can do when you are starting modeling something in GR in compare with the Newtonian. In your computer codes, you can go and take the value of the speed of light and make it bigger. Like instead of 3 times 10 to the 8, you make 6 or 12 times 10 to the 8. And what you should have is that this is my GR solution, and here in brown is the Newtonian solution. So it should happen that when you increase numerically the value of C, your GR solution goes to your Newtonian solution. And that's what I saw.
So you find over 10% in fact.
Yeah. It's going to be complicated, but yes, 10%, which is the compactness factor. But it's a bit more complicated than that, I'm sure. So this plot here, the light, it's the comparison between the GR final magnetic field with the mountain and the initial dipole. So the dipole is in broken lines and solid lines. You have my solution, final solution, the distorted magnetic field because of the mountain. So by the way, you see here that at the crust, the dipole is perfect, and then the mountain is deforming and deforming the magnetic field lines. This result was already seen in the Newtonian model, but the quantitative difference, there is a quantitative difference between Newton and GR, and so that the Newtonian deforms the magnetic field lines more than the GR case.
So Newton is dashed.
Yeah, Newtonian dashed and solid GR.
And what difference at the pole? So you go to the equator.
Yeah, but here is because by the equator you don't have the mountain, so you have a dipole, right? And at infinity you also have a dipole, but you see that the dipole value is different. So there is an increase of the dipole when you look from infinity. This plot here, just word of caution, it is a nice way to compare things, but in a way is a bit of a lie, right? You cannot say this is nature with GR and this is nature with Newtonian. Here's the difference. There is a lot of choices you have to make. How you're computing distances. Distance in the reference frame of the star is distance in the reference frame of an observer at infinity. So there are all of these tiny choices that may influence this. There is a very cool paper that I got to know later on that is called The Illusion of Magnetic Field Estimates, which is just a theory paper saying, look, if the observers say, oh, this neutron star has this value of magnetic field, but you have to
Yes.
muted. Muted. Oh, muted. Right.
So maybe you can use some unique measure that doesn't depend on the neutron source coordinates to quantify this difference, like the strength of every moving.
Yes, there is like some invariance. I've muted everyone.
Yeah, that's
Yeah,
superpower.
I have power. I will unmute everyone remotely at the end to ask questions if they have questions. But yeah, there is some invariance that you can use to compare the dipole moment value at the dipole moment value scalar you can compare. But in a plot like this, you have to make some choices. Not working. So here again is some attenuation and some comparisons between Newtonian and GR, but this plot might be better, which is the dipole moment integrated, so the actual value of the dipole moment by the amount of mass that you are accreting. So again, you accrete mass, you bury these magnetic field lines, you store them, and the magnetic dipole moment reduces. And in the GR case, you have 3 times less reduction. Again, these things sometimes depend on some choices, but this is a very interesting behavior that you cannot get by some compactness assumptions. The compactness is 10% for neutron stars, so the effects are going to be 10%. No, because that's about the accreted mass. And this is the density distribution, which is the important thing for gravitational waves. So this is a quarter of the whole space, an 8 actually, but so this is the neutron star surface, and here is the density of the mountain. Here's the Newtonian, here's the GR. It's very hard to tell, but if you look carefully, here the Newtonian one is more spread out in the angular direction than the GR case. So question for you guys to think right now, what is going to be the ellipticity? Is the ellipticity higher in Newtonian or GR? Ellipticity is when you have a ellipsoid.
It's higher in GR, it's more concentrated.
Yeah. So if you have this radius, I call it A, and this radius B, the ellipticity is approximately RB minus RA over R. Sum of the R's, right? Or yeah. So these results are summarized in this paper. And now let's talk about continuous gravitational wave. So make your bets in your head when the ellipticity is going to be higher. Okay, continuous gravitational waves. Continuous gravitational waves are gravitational waves with constant constant frequency. So they are monochromatic gravitational waves. We call them CWs. And the best source candidates for this kind of waves are rotating non-axisymmetric objects. That is, neutron star with mountains. So how does this model emits gravitational wave? So this is what they call the triaxial model. So imagine that you have an ellipsoid that is rotating through one of its moments of inertia, the axis of the moments of inertia, principally. The quadrupole moment of the system, of this master's distribution, is basically the moment of inertial tensor plus some constant terms. And for gravitational waves, what do? You take the second derivative of the quadrupole moment, right? So this constant term here is here. So what matters is actually the moment of inertia tensor of the star. So when you do this and you model this for a rotating thing, you get the sinus, like the strain is sinus function, sine or cosine. But most importantly here, I will talk, it's the amplitude. What is the amplitude of these waves? Well, they depend basically on these 3 things, or things with this moment of inertia. It depends on the frequency squared of rotation. So things that rotate faster emits more gravitational waves with higher amplitudes. Depends on the ellipticity of the system and the distance that you are from that object. And again, the ellipticity is defined properly this way by the moments of inertia through different axes. If you do an ellipsoid model, this here is a very good approximation. And I was Googling yesterday, what is the ellipticity of Earth? When I do this talk in the at IAG USP, I will ask the geologist. For now, you'll be happy with just some Google. I don't know if that's true or not, but I got this value from the internet, 3 times 10 to the minus 3. So the Earth is a bit fatter at the equator, and that's the ellipticity. If the ellipticity is 0, the amplitude is 0, right? The spherical object doesn't vary its polynomial. Sorry. X is metric, but like if the ellipticity is 0, your object is spherical. The
You could have I1 equal I2 different from I3.
that would you would also true. You could have an oblate effect. So it would be 0. And for continuous systems like I have, some mass density distribution, you calculate the ellipticity like this. And it's very cool. When I was doing this, I thought about this term here of the magnetic field. Good. So magnetic fields also carry energy and momentum. So if you have a rotating magnetic field, you would also have gravitational waves, right? So forget about mountains for a second. Just imagine a pure dipole in space and its magnetic axis rotating. That also emits gravitational waves. And I was like very excited about this because it's a purely relativistic effect. But then you also have the matter. Well, you're going to see the comparison of these two effects. So this is the ellipticity. The ellipticity is higher in the relativistic model, exactly because the mountain is more concentrated both. And look here at values of the ellipticity. So it's 10 to the minus 5, have this reference here. And this is an overestimate. But let's talk, so the difference here between the relativistic and Newtonian parameters, as people guessed, is around 10%. And what about that term of the magnetic field? How much gravitational waves the magnetic field radiates? The electricity that you get from the magnetic field is 10 to the minus 11. So 6 order of magnitudes lower than the actual mass generating exactly because of the C4 term. But here's the magnetic field energy density. Right. For the plasma people, B squared over 2 is the magnetic pressure, right? This is B squared over 8 pi. Yeah.
Well, my question is super basic because I'm super rusty at gravitational wave physics. I guess that for having gravitational information, you need some kind of quadrupole component for that.
Yeah.
And if you have a completely perfect axis symmetric system, in this case, the mountains would be basically the mount would be on top of the axis, which if it's rotating, my expected thing would be that wouldn't contribute to gravitational wave emission, no?
Yes.
So I don't know if here the thing that is contributing is like the energy density of the magnetic field, which is like offset from the.
No.
Well, my question is.
No. It's very good. I get this exact question all the time. There is a basic answer to it.
Yeah.
Have your rotating object. You have your. That's why I always draw this thing like this. This object is rotating this way.
Very well from the start.
And this is the magnetic axis.
So, is there some?
This is why these things are pulsars, right? Because
yes,
the jets, you see the jets as a lighthouse because these two axes are not.
So that being said, because of some internal equation of state within the neutron star, that it's So where's this offsetting between the magnetic, the direction of the magnetic dipole and the rotation of the neutron star itself?
It's a great question that I don't know the answer. This you would have to do some modeling of the formation of the neutron star, and basically these things are kind of in a way not aligned during the formation.
Okay.
But this is, at least observationally, is quite clear, right? You see this all the time. Earth has rotation axis and magnetic axis that don't coincide, and pulsars are observable exactly because of this, right?
Like there's like a typical angle of offsetting between one and the other. Like it's like a peak, let's say at 30 degrees or something like that.
Yeah, you can make some population estimates of all the pulsars that you know, but there's a lot of factors to consider that are biased, because if it doesn't shine into you, you don't see it. So it's a bit hard to say like what's the average inclination. What people do in this gravitational wave searches is that they take some statistics. They do lots of different angles here, and then they get some average.
I will ask later about the
Yeah.
basic questions and let you move forward.
Okay. Yeah. So, right. I also studied some what happens when you vary the compactness of the neutron star. So the compactness is this ratio between mass and radius. If I go back here, this is the relativistic correction, right? And classic of relativistic corrections depend on the mass over r, right? How far you're from this mass. So when you vary the compactness of your system, you are varying the relativistic corrections. And what you expect is that when the compactness is small, the Newtonian and the GR results are closer together. So, and this is kind of what you see. So when you fix the mass and increase the radius, the results here showing electricity, they kind of converge. And here as well, when you fix the radius and increase the mass, no wait, increase this mass, this should be actually, this is the counterintuitive thing, and they cross. But of course, this is not a perfect test like the speed of light. The speed of light test is the perfect test, because when you change the speed of light, you just change the relativistic correction. But here in the system, when you change the mass of the star or the radius of the star, this is not going to affect just the relativistic correction. It's going to affect the system as a whole.
But the dimensions GM over C.
Yeah. Yeah.
So if you increase C here, the compactness is to 0.
Yeah. That's why, like, this is in geometrized units. When you put G and C squared here, when you put C to infinity, the compactness goes to 0, and the results should be the same. Yeah. And that's exactly what I observed when you change the C. But when you change the R value is not as simple as that, because yes, you are going to put the compactness to a small value. But for example, you cannot take R to infinity. That will be a nonsensical neutron star.
Yeah, what you're really testing is you change the efficient state of the neutron star itself.
Yeah, exactly. I'm changing the neutron star periodic state, changing this M over R parameters, and seeing how this affects. But again, it's not a perfect relativity test. I'm going to finish soon, promise. So for my model, again. So from my model, this is the kind of amplitudes that you get. Sterani, I put this for you. You ask about the distance from source. There. So this is the phase value of the amplitude of your gravitational waves. if you think straight off like the sensitivity to of the detectors, you might say, this is nonsense. You're never going to observe this. But that's not quite true. But here, yeah, so you see 10 to the minus 6, a typical ellipticity, some rotation, and the distance from the source. These results are summarized in this paper that I wrote. Now, quickly, some thoughts about the search for continuous gravitational waves. This is not exactly what I do, but it's completely irrelevant. So I will just present here some basic ideas. So again, from my parameters, you had 10 to the minus 26, minus 25. This is an overestimate, again, because of the simple equation of state. I'm assuming that when you do this a bit better, this is going to reduce, like in the Newtonian case, but no one has done this calculation so far. I would like to pay me money. The theoretical and computational modeling is crucial because for the searches, because you need to know what you're expecting from each source to see if you can find these signals. And the searches in the LIGO data is very common for continuous waves. And the searches are divided kind of in this hierarchy. You have the sensitivity for computational cost. So the easiest search that you can do is the target search, where from electromagnetic observations, you know where the pulsar is, you know what the rotation frequency is, so you have a good idea of what would be the continuous wave signal, so you can go and see if you find this in the data. Then there are narrow band searches that you take the electromagnetic observables and you let them vary a bit, so that gets a bit more expensive computationally. There are directed searches, which is you have a supernova remnant that you believe that there is a neutron star there, but you don't see them in EM observations, so you don't know the frequency. So you let the frequency be whatever it is, and then you search for it, but you know the location. And there is blind searches or all sky searches, which is like, I'm not assuming anything about location. I'm not assuming anything about frequency. Where is this things? So all these kind of searches are done constantly. You see papers being published about this every time. And so far with the LIGO Virgo cargo data, we haven't seen any continuous waves. This is one example. Is the example that Ojilu talked about. So this is a all sky search or blind search, so very expensive computationally, and they look for continuous waves in this frequency range, and they didn't find any, but they say it cannot be higher than this amount of strain, because if it was, we would have seen it. Just and then you can maybe translate this to some ellipticity value if you assume distance, if you assume frequency, and then here they say ellipticity not greater than 10 to minus 8. But you see distance here, 100 parsecs, so quite close. And assuming a frequency as well, this is the best that they do. Yeah.
That was a question I just didn't read the abstract.
Okay. All right. And what about future detectors? I will talk just about the Einstein telescope. So there was this paper August this year of the science of the Einstein telescope, 900 pages. And here it is, the rotating neutron stars and continuous gravitational waves. This is one of the plots of the paper. It shows okay. So I said, 10 to the minus 26, whatever, you might think, oh, this is not detectable. But what happens? Continuous waves have a very nice property that they are continuous. So they're always happening. And this makes your analysis easier because you can take your signal and you can fold it in itself in a very basic way. And you can try to find correlations like this, putting your signal on top of your signal. So this persistence of the emission makes it easier to detect. So this here is the light, the sensitivity curve of the Einstein telescope when you integrate it over a year. So you see that
In the covalent way.
sorry,
In the covalent way.
yeah. So you see that it goes much lower than the just simple burst kind of wave, gravitational wave detection. And here is the what you kind of expect from Scorpius S1. If you say that if you assume some like spin down percentages going to gravitational waves. I won't go into the details, but this is kind of what you expect, and your sensitivity is lower than that, meaning that you would be able to observe it. And this is another plot from the paper that shows now it's thinking of all sky searches. So in an all sky search, how far can you see these objects? So depends on the electricity, of course. So if the electricity is higher, you can see these objects further away. But you see that even the electricity is of 10 to the -8, quite small electricities. You can take this. The pink area is the size of the Milky Way. So you can get all the galactic pulsars. And according to theory predictions, mine included, and others, the detection is highly probable with Einstein telescope. And again, I just love this figure. I just wanted to put at the end here. It's this animation. It's very hard to do on LaTeX, but I did it. That shows exactly this low mass X-ray binaries are prime candidates, and they would emit gravitational waves like this. And in my opinion, detection of continuous gravitational waves is one of the next big milestones of the field, but we might need further generation detectors for that. And for future work, lots of improvements can be done to the model. Again, equation of state, consider time-dependent effects like ohmic diffusion, analyze this with GRMV solver like ATK. Consider the effects of the rotation of the neutron star into the curvature. Yeah, I would like to thank the organizers for the chance of giving this talk, and all of you who have listened to the talk.
Calculation time.
Okay, good.
Thanks for the talk. Sorry, it's gonna be a bit long question, but you talk about this the amplitude, the impact on the amplitude of the gravitational waves.
The what part, sir?
When you basically show what's the impact of
Yeah.
magnetic duration on the amplitude of the gravitational waves. But what about the pulsar per se, like the beam of the neutron star? Do you have an estimation of how much this magnetic accumulation would impact on the pulsar?
Good question, because then you're trying to tie the X-ray
Yes.
emissions. Yeah. Yes, there are some estimates, but I will confess that I don't know much about those. The EM part, I was more focused on the gravitational wave.
But what you get is this roughly factor of 3 difference between the GRK and the neutron star.
Yeah. Yeah, you're going to but then this is very good, and it goes in this thing of the estimates. This difference of 3 would suggest that for it to have the same effect in Newtonian and in GR, you would need 3 times more mass or 3 times less mass. So in a way, it is like maybe you say, all right, this much mass is being accreted to the star. And then my question is, how do you know that? And the answer is, how the observers know that is that they assume some theoretical model, and the theoretical model has this formula, put the luminosity there, here's the mass, or here's the magnetic field. But these are very model-dependent things. So you would need, it is a bit harder to like, and people are not, the astrophysicists and the observers are normally not like, what is the GR formula for that? They're like, oh, basic Newton, the model will do. And for example, this is also very pertinent for dipole. What is the dipole formula? Oh, sine over R something. But what is the dipole in Schwarzschild spacetime? There is another formula for that. And so you have to solve this degeneracies. Yeah. I don't know if I can unmute people.
People should raise their hands. If anybody is,
Yeah, if anybody has questions online, maybe you can
just raise your hand and then.
Hello. Hello.
It's
Hello.
together. Yes.
Sir, myself Uday. Can I ask questions, sir?
Yeah.
So according to space-time relativity, the relativity theory, the faster we move through space, the slower we move through time, right?
Yeah, sure.
Yeah. So as Earth is a part of our galaxy, which is moving at some distinct speed in our universe, right?
Mhm.
So we have calculated the speed of light 3 lakh meter per second, right?
Yeah.
Very if we move out from our Milky Way galaxy.
Yeah. Don't know if I'm getting your question right, but yes, this
Can you repeat the question? I didn't hear.
from what I understood, he's asking about the relative motions between you and the source of the space that would modify what you observe. Yes, there's this. I don't know if that was your question. You can correct me if not. But when you model these continuous waves, because they are so long, like they are monochromatic, persistent signals, you have to start considering the modulations that happen with Earth going around the sun going around center of the galaxy, and yeah.
I think you misunderstand. I'm exactly saying like as our Earth is moving continuous, Earth and Sun and solar system is moving through the Milky Way galaxy, right?
We are in the Milky Way galaxy.
No, but that's not on the time scale of the year.
Yeah.
The movement of the sun in the Milky Way is a much longer time scale. We observe for years.
Yeah.
That's negligible.
Exactly. So we are moving through space through a certain speed. So time must be dilate, right?
Yeah. Serenity to
Like time dilation, sir.
Yeah. So with respect to what observer.
Yeah. So time should be dilated, right? But so time dilation and the speed we calculate relative to our time.
Yeah.
Can you understand what I'm trying to say?
Are you trying to say that the speed of light that we measure would be different?
Yeah, I mean that out of our solar system there should be a different constant of light.
No, but then relativity says the speed of light is the same value irrespective from this. It's not pertinent for the topic.
I think we have to move on.
Yeah.
Any other questions? So I have a question actually. It might be speculative, but if you say that you took into account the energy, the contribution of the electromagnetic energy to the quadrupole, so why not consider the contribution of the angular momentum to the magnetic multiple? So is there any simple way to compute the angular momentum of the electromagnetic field? I understand it might be ultra small, but just as much as possible.
No, but we do like you do consider that's the braking, the electromagnetic braking that they call for.
No, the angular momentum of the electromagnetic field.
Yeah, so that's how a jet.
Braking and slowing, you mean?
Yes,
not
yeah, braking fluid.
Okay.
Which, by the way, there is this thing. So you can write an equation. And so the spin velocity of the neutron stars are changing with time, right? They are braking, so that
They're slowing down. Sorry for
braking and slowing down. Yes, this not negative. So you have a negative value here, and this is a general ODE that. Depending on your emission mechanism, your loss mechanism, you have different values of K and N. Then when you do the theoretical calculations for gravitational wave emissions, this N value here is 3, I think, or is the other way around. But this is 3, and the electromagnetic field, you compute the amount of angular momentum that the magnetic field is extracting. You have another N value of 5 here. And then what you can do is, and you have different amplitude values, right? So the gravitational waves is going to take much less power from the system than the electromagnetic. The electromagnetic takes much more.
Okay.
But when you take our population of pulsars in the galaxy and you try to fix something like this, the fits, a lot of fits say 100 and you go equals 100, and we have no idea. Yeah, we have no idea why is that value. None of the electromagnetic value or the gravitational wave theory predicts this 100. Is called anomalous break. This is called the breaking index, and it's called the anomalous break index problem. And people there in Australia were also working with that. Andrew has some ideas about it.
But it's not too difficult to compute the contribution.
No.
To angular momentum.
No, it's not. You can do it, and you're going to get something like this with n equals either 3 or 5. I don't remember.
And I was wondering in terms of the number of sources. So you have Astro on the top in relation to the gravitational wave of sources.
Yeah.
So you started by making a distinction between the mountains with a crust condition, glassy mountains, and those that you discussed. So in your case, you need a binary system, right? Because of the application. And I don't know what's the fraction of neutron stars that at least we can observe electromagnetically that are in the binary system with respect to the
Yeah, I also cannot answer that question, but this is more of a question for the astronomers. But I know roughly that I might be wrong, maybe search this later. But like the number of total pulsars that we observe, it's around 1,000, or maybe 1 order of magnitude off, I believe. And then 1 order of magnitude lower, you have this binary systems.
Okay, so it's a tenth of all known potential systems.
Yeah. In this paper, by the way, the Einstein telescope paper, if you open there, it has a table of how many sources you would expect to be in continuous gravitational waves. And then they consider like how many sources would you detect with Einstein telescope. And then they consider a few different cases, like worst case scenario, best case scenario, and that those numbers come from exactly the amount of binary neutron stars that we have, the amount of isolated neutron stars or magnetars. Yeah. Check what's there.
Sorry, because I be very basic, but so one of the other fundamental symmetries that this thing has. It was the relation of the accretion disk with respect to these other two angles, no? Which, for what I understand, they are independent in the sense that the thing that would create the mountain would be just determined by the direction in which the dipole. No.
Yeah.
So is it relevant somehow where the accretion disk lays with respect to these two things, or at least observationally, or has any kind of impact, or is something that one can disregard completely? And
No. It has an impact. By the way, this thing. So, say, pictures are hard. You have the accretion disk here, right? And then you have your dipole. There is a dipole line that is going to just touch the accretion disk. In our models, we call this psi A. And all the other ones here, they're going to pierce through the disk, right? So when we assume n of psi, we put most of the mass inside this psi A value, right? Because the mountain is going to be far there. But if you then take, because normally accretion disks are perpendicular to rotation.
independent of the position of the star with respect to, because I can imagine that you have the neutron killer star rotating this way, but I guess that configuration might be weird, but if the star is moving in this direction, I would expect the accretion disk to be completely aligned with the. Well, what I mean, imagine is that the accretion disk is.
Yeah.
With
No,
respect to
you're
the star. With respect to,
okay. I don't know a lot of this accretion dynamics things. I know that this is relative, like normally they're relatively perpendicular. It could be off. Maybe this is a bit inclined. But in your question of if this is relevant at all, it is actually is because the mountain forms in the magnetic poles, and when you rotate in the angle that's like not 90 degrees, like what is the best case scenario? The magnetic pole of the neutron star is laying down and getting met directly here, so you have the ellipticity perpendicular to the rotation axis, and that's maximum gravitational emission. But normally you don't have that case. You have something like that. And what happens is
when your model would be entering on the problem that you assume for
You-
MO side.
what, sir?
In your model, it would be entering through the prescription that you're providing in MO side.
Yes, exactly. What happens, like this triaxial cute model that I showed you, is for the star rotating in along one of its main moment of inertia axis. But as I was saying, this might not be the case. This might be here, rotating through here, and what you have is a precession movement. And this precession movement also would emit gravitational waves, continuous gravitational waves, and it would emit at the rotation speed. This here I didn't say, but like the rotation frequency and the frequency of gravitational wave, they're related by a factor of 2. The gravitational waves are emitted at 2 times the rotation frequency. But when you have precession movements like that, they emit at exactly the rotation speed. So you would see maybe like in frequency amplitude thing, you would see 2 bumps, one at the rotation frequency and one at 2 rotation frequencies. And this is actually very relevant because in this narrow band searches, or even in the high searches, they search in those 2 frequencies normally, the rotation frequencies and the twice the rotation frequency. And they also search in the 3/2, something like that, because it's a oscillating mode of a fluid star. of like the star pulsating kind of something like that. I don't know. It's a non-nuclear multiple. Yeah, it's called F mode or NR mode missions. Look at that.
Okay.
Sorry, I got in a decent defense, but let me just, have everyone, he's walking, just arrived, just 3 days ago. The studying postdoc that, was sick, and he will be talking this afternoon, but since we are having lunch now, I just wanted everybody to meet. So,
Nice to meet you.
you're welcome to walking, correct? But don't give a talk, yeah.
My chance to ask questions.